Here we're going to consider colligative properties. Colligative properties are properties of the solvent in solutions. There are four colligative properties: vapor pressure lowering, freezing point depression, boiling point elevation, and osmotic pressure. Now, in terms of vapor pressure lowering, we already considered that thermodynamically, and we ended up for an ideal solution, Raoult's law, meaning the pressure of some component above the solution is equal to the mole fraction of that component in the solution times the vapor pressure of that pure component. So the mole fraction always has to be less than 1 or less than 1. So therefore the vapor pressure of a solution will always be less than a vapor pressure of the pure component. And that's Raoult's law, vapor pressure lowering. Let's look at freezing point depression. Now remember from introductory chemistry, this equation was just sort of thrown at you. The freezing point depression was equal to this molal freezing point depression constant, Kf, times the molal solution concentration. What we're going to do here is to get this equation by some more fundamental thermodynamic considerations. So what I want to do is to make the argument that here we have, I'll put open circles to be the solvent. There's our solvent. And then within the solvent, we have these filled in circles, and those would be the solute. And we're going to say that we have much more solvent than there is solute. So the solute would be the component that's in lower concentration. Let's consider this sort of pseudo reaction. Let's call the solute A and the solvent B. Let's take the solid of the solute and let's take some solvent. That's a solvent. And we're going to take some of this and solvate it. So now we have AB, which is solvated. So for example, if you dissolve something in water, say sucrose or something, sucrose then would be dissolved. It would break apart from the solid and be individual molecules, so these would be sucrose molecules. And like we did for when we considered the temperature dependence of solubility, here we're going to consider boiling point elevation. We're going to consider this as just a liquid. The solute now is a liquid dissolved in the solvent liquid. So it's like a liquid-liquid solution. I think what we can immediately say, if you like that argument, just go back in the previous part of this lecture, lecture 12b, and look at that derivation. And what we found there was that the natural log of the solvent concentration expressed in mole fraction, actually what we're looking at the solute, but here we're looking at the solvent because we want to look at the freezing point depression of the solvent. So initially the solvent is pure, but now because of this extra, quote, liquid we got by dissolving the solute, solid in there, the mole fraction of the solvent has gone down. Well, analogous to what we did before, the natural log of the mole fraction of the solvent will be the enthalpy of fusion divided by R, 1 over the temperature minus 1 over the freezing point temperature. All right, so we're making an analogous argument to the argument we made when we considered the temperature dependence of solubility. So that's where we're going to start. Might review that and look at the similarities. We really want, I don't know if we really want to do it, but what people usually do is to express the concentration not of the solvent but the solute. For a two-component mixture, the solvent is 1 minus the mole fraction of the solute. So that would be equal to minus delta H of fusion over R, 1 over T minus 1 over freezing point. This would be the freezing point of the pure solvent. Maybe you've heard about Taylor series, and maybe you heard the expression for mathematicians, Taylor series is your friend. So what we want to do is to expand this expression in a Taylor series about the point x equals 0. So just to refresh our collective memory, a function x be expressed as the sum for I equal 0 to infinity of 1 over I factorial, the ith derivative of f with respect to x, evaluated at the point x equal x0 times x minus x0 raised to the ith power. So this expands a function about some point x equal x0. So let's expand the function f of x equal natural log of 1 minus x solute. I'll just omit the solute here, but remember that's solute, about x equals 0. So let's take the first term, this Taylor series expansion. That means I is equal to 0. So for I equals 0, we have 1 over 0 factorial. The 0th derivative of f with respect to x, evaluated x equal x0. That should be a 0 down here, I guess. And then x minus x0 raised to the 0th power. We know from factorials this is equal to 1. This, the 0th derivative of the function, is just the function. The function is ln of x, so ln of 1 minus, and we're going to evaluate this at x equal x0, and we said x0 was 0. So we'll just evaluate this x equals 0. So 1 minus x, 1 minus 0. That's what that term is. And this term will be x minus 0 raised to the 0 power. All right, this is equal to natural log of 1, which is 0, and this is equal to anything raised to the 0 is 1. So this, the I equals 0 term, is equal to 0. Now let's do the I equal 1 term. Again, what we're doing is we're just taking the first two terms in this expansion. So I equal 1, we'll have 1 over 1 factorial, the first derivative of the function with respect to x, evaluated at x equals 0, and we have x minus 0 raised to the first power. This is equal to 1. The derivative of f of x, recall that f of x is ln of 1 minus x. So when you take the first derivative of here, we get minus 1 over 1 minus x, and we're going to evaluate this at x equals 0, so that's a 0. And here, that is just x. So we multiply all this out. The I equal 1 term gives, this is a minus 1 minus x. So what this means is the natural log of 1 minus the solute mole fraction is just equal to minus the solute mole fraction. All right, so that's a handy thing to be able to work with, those Taylor series expansion. So we go ahead and substitute that in our equation a while back. So we get minus x to the solute. That's equal to minus delta H fusion over R, 1 over T minus 1 over T freezing point of the pure substance. This will be the freezing point of the mixture. What are we going to do? Now let's cross multiply. So if we cross multiply, this term will be freezing point minus of the pure stuff minus the freezing point measured over T minus T times TF. And let's get rid of that minus sign on both sides. We get that the mole fraction of the solute is equal to delta H of fusion divided by R times the freezing point of the pure solvent squared times the freezing point of the pure solvent minus the freezing point of the solution. And this we're going to call delta T, the freezing point depression, the lowering of the freezing point. So there it is, but it's not quite yet in the form that was presented in introductory chemistry. The mole fraction, or the mole fraction of the solute into molality. We did that once before. Let's do it again. So the mole fraction of the solute is equal to the moles of the solute divided by the moles of the solute plus the moles of the solvent. And we're going to say that's about equal to the moles of solute divided by the moles of the solvent when we have a dilute solution. Dilute solution means the moles of the solute is much less than the moles of the solvent, so this sum is about equal to the moles of the solvent. Now, recalling what molality is, so molality is moles of solute per kilogram of solvent. We compare these two units. Looks like the numerator, moles of solute, is okay, but we got to convert moles of solvent to kilogram of solvent, and we do that by multiplying by the molar mass. So this is moles of solute over moles solvent, and we multiply here capital M, molar mass of the solvent. So molar mass of the solvent, it's expressed, say, in kilogram per mole times moles of solvent. This term then will be kilogram of solvent. And then therefore this term, these terms here, will be equal to the molality. Our conversion factor, X of the solute, the mole fraction of the solute, is equal to the molality of the solute. I don't need to put that there, that's what's implied, times the molar mass of the solvent. And so now that we know that, we can convert this concentration in terms of mole fraction to molality, so that M times M, that's the mole fraction, lowercase m molality, uppercase M molar mass, that's equal to the enthalpy of fusion over R times the freezing points of the pure solvent squared times delta T, or delta T is equal to the molar mass of the solvent times R times the freezing point of the pure solvent squared divided by delta H of fusion times the molality. And if we define these terms here as Kf, we have the introductory chemistry expression delta T, the freezing point depression, is equal to a constant Kf times the molality. And what have we done to get that? Well, we've assumed that we have a dilute solution, and if it's a dilute solution, then the freezing point didn't change much with when you add the solute, so this can be replaced by a constant. And with those things, we have the introchem equation. And the key point, again, what we did was, when we did that derivation, used Taylor series, that's kind of cool, is that we assumed that the solute was a solid, but then when it dissolves, you can consider that just as a liquid. So the solute going from the solid to a liquid gives you delta H of fusion. So that takes care of freezing point depression. We know where that comes from thermodynamically.